The wave speed of a wave is the speed at which energy is transferred by the wave. Here's an example of a wave. Matter vibrates in order to transport energy without the matter moving overall. In this case, the matter moves up and down so that energy can be transported in this direction. The wave speed tells us how quickly the wave can transport this energy from one place to another. It's important that you understand that this is different to the wave's frequency. Frequency only tells us how quickly the waves are being produced, but it doesn't tell us how quickly it carries energy. Now, what's the simpler way of visualizing wave speed? Well, we see this as the speed at which a point of the wave is traveling. Let's look at our example again. As we can see, this pattern is moving along to the right. We can use the speed at which it's moving to give a value for the wave speed. For example, we could follow the peaks as they're easy to keep track of. Then we just ask ourselves, how fast are the peaks moving? Though remember that this is not the matter that's moving, but rather this pattern that forms as the matter moves up and down. But is there another way we can calculate this speed? How does speed relate to the other properties of the wave? We can deduce wave speed from the time it takes a point on the wave pattern to travel one wavelength. Here's another example of a wave pattern. Let's focus on this peak here and see how long it takes to travel one wavelength. Remember that a wavelength is the distance after which the pattern of the wave repeats, or the distance between two equivalent points on the wave. In this case, a wavelength would be the distance from our peak to the next peak, and we can label this wavelength using the Greek letter lambda. Now, how long would it take our point to reach this line one wavelength away as a wave moves like so? Well, to answer this, let's recall another definition. The period of the wave is the time it takes for the wave to repeat its cycle of motion, or it can be measured as the time it takes a point on the wave to travel one wavelength, which is what we just saw. So this motion must have taken t seconds, where capital T represents the period. So how can we then use this to find the wave speed? First, let's remind ourselves of the general equation for speed. That is, speed equals distance over time, which we can write as v equals s over t, where s is the distance travelled and lowercase t is the time taken. Now, how does this equation apply to the motion we just observed? Well, we watched a point on the wave travel a distance of one wavelength, so let's set s equal to lambda. Then we deduce that if the point travelled a distance of one wavelength, then the time taken must be equal to the period of the wave. So we can set lowercase t equal to uppercase T for period. It's a bit confusing, but here lowercase t and uppercase T are different things. Uppercase T represents the period of a wave specifically, while lowercase t is just time in general. So we've found that the speed of the wave is equal to its wavelength divided by its period, but we can simplify this even further. Remember, we can relate the period of a wave to the frequency of the wave with the equation f equals 1 over t. We can then use this to rewrite our speed equation, since this shows that dividing by the period is the same as multiplying by the frequency. So we rewrite this equation as lambda f. So overall, we have that v equals lambda f, which means that the speed of the wave is equal to the wavelength multiplied by the frequency. For your exam, you should be able to define the term wave speed and understand where this relation comes from. Let's quickly go through the typical units for this equation. Wavelength is a type of distance, which we measure in meters. Then frequency is measured in hertz, which are the same as 1 divided by seconds. So if we multiply meters and hertz together, we get meters per second, which is what we'd expect for a speed. This is a very common equation used in wave problems in exams, so let's do a practice example with this. A child pushes a slinky spring back and forth to produce a longitudinal wave with wave speed 1.2 meters per second. The distance between two adjacent rarefactions in the spring is 0.3 meters. Calculate the frequency of the waves in the spring. Remember that longitudinal waves are waves where matter is moved back and forth instead of up and down by the wave. We'll have the same relation between wave speed, wavelength, and frequency though. So for step 1, write down the key information and check the units. So we're told that the wave speed is 1.2 meters per second. Then we're told that the distance between two adjacent rarefactions in the spring is 0.3 meters. The distance between rarefactions is the easiest way of measuring the wavelength of a longitudinal wave, similar to measuring the distance between two peaks on a transverse wave. So this is telling us that the wavelength is 0.3 meters. Both of these are in standard units, so there's no need for conversions. Now we need to use this information to find the frequency of the waves. In step 2, rearrange the wave speed equation to make frequency the subject. Now our wave speed equation is wave speed is equal to the wavelength multiplied by frequency. To make frequency the subject, we want to move wavelength to the other side of the equation to have frequency on its own. We can do this by dividing both sides by wavelength. This gives wave speed divided by wavelength is equal to the frequency. Then in step 3, substitute in the values to calculate the frequency. If we flip our equation from the previous slide, we get that frequency equals wave speed divided by wavelength. The wave speed was 1.2 meters per second, and the wavelength was 0.3 meters. So substituting this in gives that frequency is equal to 1.2 divided by 0.3, which gives a final answer of 4 Hertz.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!